Okay, so welcome to Calculus 25-028. This is really a multivariable calculus course, I should say. So a better name for this is multivariables calculus. So I guess the first order of business is, have you all read the course outline, and do you have any questions about course outline? You can ask your questions, or you can post your question if you want. Yes? So yes, there is a question. Will the lectures be recorded and posted on all? Yes, that's the plan. But okay. Any other questions? So about marking, I guess everything was clear, right? We are going to have a midterm, which will be more or less end of October. And this midterm will be roughly kind of covers end of chapter 3, more or less, by the end of chapter 3. So that's, I guess, is 30% of your mark, final mark. And there is a final, which is cumulative. It contains everything. And that is 40%. And there are 3 assignments, 3 sets of assignments. So each assignment roughly will cover 1/3 of the course. So you can imagine the assignments are going to be kind of larger than normal sets of assignments. But you will have more time, of course, to hand in, submit your answers for those assignments. So the assignments is, of course, 30%. The remainder of your final mark. Now, one thing you want to notice, maybe I already emphasized, that the book has changed this year. We are not using Stewart, right? Stewart's calculus, multivariable. Beg your pardon? Stewart's multivariable calculus was used for several years. We thought actually single variable, multivariable course instructors, all of us in both departments, decided that it's perhaps time to switch to a new book. And the book that we chose is OpenStack's book. As the name suggests, it's freely available. It's a collective publication. A lot of mathematicians, very good mathematicians, have contributed towards that. And as a result, it's free. The online version is free. So I have put a copy of that online version PDF file in the on OWL. You have access to that. You can also download it anywhere in the world if you want. So that's completely free. So that's one good thing. I thought it would help to have not to pay like $150 or something for this course and for this textbook, I mean. The book is pretty good, actually. Beg your pardon? Can you type your question, please? I couldn't hear you, if there was a question. Anyhow, so that was the, that's about the book. So the book is actually kind of slow pace. I mean, it's like 1,000 pages, 1,100, almost 1,100 pages. So it's very slow pace, but it's good because everything is kind of explained, but not over-explained. So the questions are formatted in a kind of easily readable way in the text, and problems and examples, and the whole theory is developed in good steps, easily accessible. So I highly recommend you read the book before coming to lecture. And of course, attending lectures is a very, very good idea, because my lectures will be different from the book. I mean, I will give my own kind of approach to the subject, and so the book is your kind of secondary resource. So you may gain a lot by attending the lectures. Any questions? Okay, so it seems there are no questions. Okay, what else we need to cover? I mean, so I guess if you don't have any questions, maybe we should start. I should start lecturing about the content of this course and what's involved in this course. So this multivariable calculus is a very, very interesting topic. So the course is, it has kind of two components. First of all, this multivariable calculus so multivariable means that in calculus that you did, in one variable calculus, we just looked at one-dimensional space and functions on one-dimensional space, which is functions of one variable. So this was one variable calculus. It was about these functions, one variable functions, and a derivative of such functions, and integrals of such functions. Basically, it was kind of interplay between derivative, integral, and this function itself. Right, so this was one variable calculus. So you learn how to maximize or minimize functions using the derivative, making derivative equal to 0. You learn how to calculate velocities of particles moving on the line by taking derivative. You learn how to compute area under a curve, and then the fundamental theorem of calculus related this to that. So this was the beginning of calculus. What we are doing, so this you did already. What this course is all about is now all of a sudden we go to multivariable calculus. So instead of functions of one variable, now we are looking at functions of 2 variables, 3 variables, 4 variables, even more. There is nothing to confine you to just work with 2 and 3 variables. In this course, we will work mostly with functions of 2 variables, 3 variables. Not necessarily just 3 variables. Sometimes the things that we develop actually work for functions of n variables as well, right? So we develop tools to deal with these functions of n variables. And so you see, all of a sudden things become extremely, or exceedingly, I should say, complicated, right? Because here we have only one variable. Now you allow many, many variables, and there's no end. It goes on. So that's a big difference, right? Between one variable and multivariable case. So this is.
Sorry, the right side of the board we can't see.
Oh, sorry. Yes, maybe I should. Oh, yes. Can you see now? Is it better? Okay, great. Thanks for mentioning this. Yes, that's so that's the. Yes, I should have noticed that. Yes. Okay, so now actually, I guess that's the limit here, right? Okay. Very good. So, so that's as far as functions goes, right? Now, instead of these derivatives, also, we have partial derivatives. So we're going to work with and define partial derivatives. So now df dx is going to get changed to be del f del x del f del y del f del z, etc. So these derivatives we are going to call partial derivatives. Okay. So I mean, these are kind of similar, their definition to this, but because we have so many of them, it's going to be more complicated, of course. And then we develop tools for also, I mean, in the second part of this course, which I won't be teaching, someone else is going to teach that. In the second part, you will learn how to integrate these multivariable functions also. So, but that's further on, not yet, not in this course yet. So that's as far as this, and then also you learn how to maximize and minimize these functions. And then we will do maximum, minimum subject to constraints, which is new. Lagrange multipliers, for example, that's a new thing that has no counterpart in one variable calculus. So these are this is more or less covers half of the course. And then the second half is about vectors, and basically is about vector calculus or vector analysis. So that's one part. Second part is vector analysis. Okay. So this vector analysis is also extremely interesting and extremely useful topic. So in physics, engineering, of course, mathematics, economics, many different fields of sciences, this vector analysis is amazingly useful. So we will learn about vector fields. And examples of such vector fields. And then we will learn how to differentiate and integrate such vector fields. So in this case, we will see some totally new phenomena when we are dealing with these vector fields. So things that we are going to work with, these are these operations of, say, divergence. Operation of curve, which So divergence will tell us how much expanding or contracting a vector field is. Operation of curl or rotation tells us how much rotation is in the vector field. For example, if you have a fluid flow, this curl will measure how much vorticity is in the flow. If there's going to be a tornado somewhere in the air movement or in the flow movement, fluid movement, it's going to be measured by this curl and this divergence and the relation between the two. And of course, we have another operation which is even kind of appears before this. This is gradient operation. So, right, so this is the vector analysis. Of course, the vector analysis is based on vector algebra. That's the first thing we are going to develop. So the chapter 2 that we are going to immediately start today is the algebra of vectors. I'm sure you have seen the many aspects of algebra of vectors. So chapter 2, as I said in my course outline, in our course outline, chapter 2 is more or less, I would say half of it, 60% of it, you're totally familiar with. You have done versions of this in linear algebra, maybe 1600. Definitely in 1600, you have done some operations on vectors. And also in your physics courses, maybe physics 1 course, you have done dot product, cross product, some versions of it, if not in high school. But it doesn't matter. If you haven't seen it, that's okay. We are going to develop it, but at a little bit faster pace. Of course, if you have questions, you will ask questions. That's not a problem. So so when we do all these things, we learn all this stuff. At the end, then we will have some great applications of this stuff. For example, one of the highlights of the course is where we take Maxwell's equations and then we apply what we learned about vector analysis to draw an amazing conclusion. So a high point in this course is that we will take Maxwell's equations that I will write it down for you later on, that doesn't matter. So that's what we take from physics. We don't prove or we don't develop these Maxwell's equations. We just take them as facts from physics. We just write them. But then we apply what we learn in this course as vector analysis. To draw an amazing conclusion that Maxwell derived around 1860, that light is electromagnetic wave. So light is electromagnetic wave. This was done by Maxwell himself around 1860s. He wrote a few fundamental papers on electrodynamics, electricity and magnetism in 1860s, and one of the highlights of his work was that he actually was able to convincingly show that light is electromagnetic wave. So that's really amazing, because up to that point, people thought that these two things are totally different. There is electromagnetic things and there is light. They have nothing to do with each other. But using vector analysis, not quite vector analysis, a kind of, I would say, a kind of earlier form of vector analysis, which actually is harder if you don't know vector analysis. If you want to do it the way Maxwell did it, it's very, very hard. It was amazing that he did it, but he was an exceptional person anyhow. So Maxwell did that, and then his prediction was confirmed about 20 years after that, after around 1860. This was Hertz's creation of electromagnetic waves using these ideas. So this is one of the high points of this course. I mean, you will see this maybe in your physics courses later on, or maybe you can study, but we will just touch the surface. This is not what, we are not doing physics in this course, of course, we are doing mathematics, but the point is that what you learn has amazing applications in many things, and that's what I want to emphasize. Okay, so any questions or comments maybe you have, or? No? Okay, very good. So we can continue. Actually, we can stop now. So this was a kind of outline of the course. Now I can start. So the chapter 2 in your book it's about these vectors in 2D and 3D, right? So vectors in 2D. When I write 2D, I mean 2 dimensions, and 3D, I mean 3 dimensions. So we are going to recall some of the basic notions. What is a vector, and what can you do with vectors, and why we need vectors, why they are useful, stuff like that. So, of course, a vector, so I believe this is perhaps in 2.1, I guess, yeah, obviously. So what is a vector? So a vector is we can think of it as a geometric object, right? So we have one initial point, and we have one end point, but that's not enough. If you just have initial and end point, then you have just a straight line between these 2 points. But there is also a direction that tells you if you are going from this point to that point or vice versa. And if you do it each way, you're going to get different vectors. So that's, this is P, this is Q. So you can say, okay, a vector in space is really specified by 2 points, P and Q. And if you specify what point is first, what point is second, then you can say, okay, I'm going from P to Q. The direction better be in this direction. So vectors then, as a result, have a length and also a direction. So it's a kind of complicated object, right? It's not specified just by one number. To specify a vector, you have to specify some data. What is this point P? What is this point Q? And if you're going from P to Q or Q to P. The reason that vectors, as you know, was introduced is because some quantities in nature and in mathematics also are actually vectors. So, vector quantities. So the simplest one you have seen, I'm sure, is velocity, for example, is a vector, right? You may complain, and you're right to complain. You might say, hey, when I drive the dial on my car, it just says you're going 100K or 80K or 140. Well, I hope you don't drive 140. But K, right? And you don't see a direction. And well, the thing is, what is shown in the dial in your car is actually not velocity, it's the speed, is length of the velocity. If you want to know what is your velocity, you have to know more information. The direction your car is moving, and is it moving this direction or backward, things like that. So velocity is a vector. So I just say here speed is the magnitude of velocity. Is a scale. Okay? So let's not confuse velocity with speed. They are different things, right? Speed is much simpler. Velocity is a vector, is more complicated. And by the same token, you can also talk about force. Force is also a vector because I have to tell you I'm applying force in which direction and by how much. So once you know both, then you know the amount of force. Another quantity which is a vector is acceleration. Okay, so that's also a vector. Or vectors as well. Now, so when we discuss vectors, I meant to also say that there are some simpler quantities, as you know, that are not vectors, that are expressible only or can be measured only with one number. Well, that number could be positive, could be zero, could be negative, right? So those quantities are called scalar quantities, right? So vectors and scalars. Okay. So scalars, it's just a number. It's just a real number. That's a kind of fancy way of talking about numbers. Just a number. I would say a real number for now. Okay. Now, scalar quantities, you know, like mass, for example, length, temperature, are scalars. So to specify temperature in this room, at least at each point, at each moment of time, you don't need to give me the direction. You don't need to give me the anything like this line from P to Q. You just have to give me a number, and we agree on some unit of measurements for temperature. For example, Kelvin. I say this room temperature is 32 Kelvin, which is not now, but let's assume, or 67 Kelvin, for example. Things like that, right? One real number gives you the value of your scale. So there is a big difference between vectors and scalars. So that's what I wanted to say. Now, what can we do with vectors? As you know, vectors can be added and can be multiplied and scalar multiplied and all that, right? So now there is some complication about vectors that we have to be aware of. The complication is this. When you talk about a vector from P to Q, this P can be any point in space, and Q can be any point in space. So it looks like to specify a vector, you really need these 2 points in space and the direction, whether you go from P to Q or Q to P. Right? So this makes working with such vectors kind of hard, actually, because you really need 6 numbers to deal with these things, right? So there is 3 numbers for this point P, 3 numbers for this point Q, and you have to say P or Q, which one first. To make life easier and to make it more kind of friendly for calculations, we make an agreement that we are going to work with vectors that at the original point, the origin of the vector is at the origin of the coordinate system, okay? So these are called, I call them base vectors, but I guess the book has some notation, terminology for them. Yeah, standard position vectors, right? So convention is this. So standard position vectors so you're going to draw a coordinate axis for yourself, x, y, z. And you put the origin of your vector at the origin of the coordinate system, okay? And then Q, the other point could be any point in a space. And notice that now with this convention, with this method, you have gained a lot. Of course, you are losing something also, but you have gained a lot. Namely, all you have to do to specify a vector, so let's call this vector A, is to give the coordinates for this point Q, right? Because the original P is always at the origin, right? So in this way, we can say that, so vector A can be specified by 3 numbers, which are coordinates of this point Q, right? This is a great convention. You'll see why. You see now, so A, I can write it as A1, A2, A3. And conversely, any triple of numbers A1, A2, A3 defines a vector, which is this vector PQ, right? So I'm going to use alphabets A, B, C for vectors. That's kind of helps me to just write easily like that. Okay, so that's one convention. Now there is one vector which is very important, and that is the 0 vector. Okay, so the 0 vector, well, we denote it by 0. Sometimes people put a arrow sign, vector sign, but we don't do it. We just say 0. And that has 3 coordinates, 0, 0, 0. So one thing you should notice is that this zero vector is different from zero number, right? They have more or less the same notation, but this one is 3 zeros, but the zero scalar is 1 0, and they are different quantities, right? So we have to make a distinction between them. So that's one thing you should pay attention. And then, so that's with that. Now, scalar multiplication. So lambda A is equal to lambda A1, lambda A2, lambda A3. So this is for any scalar. I usually denote the scalars by lambda. I don't know why. Well, I know why, but that's for any scalar lambda. I use Greek letter lambda belonging to R. I suppose you understand this notation. I'm going to use some notations like lambda belonging to R. I hope it's okay. Okay? All right, so if you don't understand this notation, ask me, I will explain this. But this just means belongs to, lambda belongs to R. Okay, very good. So we have that, then what? Now another operation, so this is a scalar multiplication operation. Another operation is addition. Of vectors. Now, if you're adding vectors, that's what you're doing, really, right? So by vectors here, we really mean these standard position vectors, right? So you have this A, and you have this B, two vectors, both starting at the origin. So what is A plus B? By A plus B, as you know, we mean the following thing. So you just go to at the end of A, and then follow by a line which is parallel to B, and then you reach a point. And then this point is going to be your A plus B. So this is the result of A plus B. So you go by A, and then follow by not B exactly, because you cannot, if you are at the end of A, you cannot follow this B. But you can follow by something parallel, and then you end up at this point is A plus B. Now you notice something very interesting already happens, because we are working with parallelograms here, right? So if you follow B and then follow A, you're going to end at the same endpoint. This is properties of parallelograms. So this is equal to B plus A. Okay, very good. So we have then these properties of additions and scalar multiplications. So I'm going to write here. Okay, so properties of additions and scalar multiplications. Okay, so these are, well, I mean, one of them I just mentioned, A plus B equal to B plus A. This has a name, it's called commutativity, so, or it's commutative property. I would call it commutativity. Good to know this. So if you add A to B, it's same as B to A. This is not obvious, right? Because these are not numbers. We had to use some geometric arguments. But if you write it in terms of components, that becomes obvious. So there is another property like a plus b plus c is equal to a plus b plus c. This is associativity. And then we have things like lambda times a plus b equal to lambda a plus lambda b. This is called distributivity. Distributive property. And also lambda plus mu times a. Now these are two scalars, lambda and mu added, get another scalar times a. That's equal to lambda a plus mu a. Both are distributivity. There is one crucial property that if you multiply lambda by zero vector, is going to get zero for all lambda. So this, my notation means for all. I hope it's okay I use this. You allow me to use this because that saves me some extra writing like that. For all, this is the inverted A means for all. So this is zero. And also 0 times A is also equal to 0. This is for all A. You see, notice this is different. Here 0 is a scalar, A is a vector. Here lambda is a scalar, 0 is the zero vector. So, but the result is always a zero vector. And some properties. I want you to read that section 2.1 carefully, where these properties are actually listed. Yeah. Do you have any questions by any chance? Or? I guess you have seen this stuff. Okay, so so I think one of the things that shows that vectors are kind of interesting. Yeah, so one of them is the length of the vector. So let's define the length. So I erase this part. Length of a vector. So the notation that we use is double line, this A, right? Double line A. Sometimes it's also called the norm of A, but you just say length of A. That's by definition square root of A1 squared plus A2 squared plus A3 squared. Okay? So we can say, similarly, you can say norm A squared is just A1 squared plus A2 squared plus A3 squared. So that's the length of, the idea of length of a vector. Of course, this really measures the length of this, so this is vector A, length of this line from O to P, so that's this length is a scalar. As the name suggests, I said length is a scalar. Indeed, it's a scalar. So after this, we are going to start then talking about inner dot product. So that's where things get interesting. So let me. So basically, this is we just went over section 2.1. I mean, to be honest, I didn't even touch section 2.1 because section 2.1 does vectors in 2D. You already, we started with sections in 3D. So if you know 3D, you already know 2D. So there's no point of so, but what we are going to do next is start to talk about the dot product. So that's the right. So if you have two vectors A equal to A1, A2, A3, B equal to B1, B2, B3, the dot product A dot B is defined as A1, B1 plus A2, B2 plus A3, B3. Okay. So one thing you have to notice is that oh, there are some questions I totally missed. Is there a mistake with the associativity example? I didn't give, oh, did I? Oh, maybe, okay, so associativity is this first part. A plus B plus C is equal to A plus B plus C. If I wrote anything else, that was my mistake. Sorry about that. Thank you for mentioning. Maybe I wrote A plus B plus C equal to A plus B plus C. So that's associativity. Okay, very good. Yeah, there is a correction already mentioned in the chat. Yeah, I think there is also a confirmation for associative. Yes. Okay. Okay, so I guess the issue is settled now. Very good. Thank you so much, guys. So I think it's a good idea you start reading now section, I would say 2.3 or 2.4, where dot product starts popping up. So read up that section, and on Friday we will meet and we'll discuss dot product. So dot product is very interesting operation, and it's very important to know what is it that this is trying to measure, because it's a kind of a strange operation. You have two vectors, A and B, and then you get a scalar all of a sudden. It's a scalar. So we have to understand what this number has to do with these two things, these two vectors A and B. I mean, how can you tell by looking at the picture what the value is? It turns out sometimes you can say a lot about this number by just looking at the picture. Sometimes, not exactly, but sometimes you can. So this is the kind of issues you have to think about it. And we will follow up from there. So guys, thank you so much. It was a pleasure to start this course. I really enjoyed starting the course like this. It's challenging. I know it's difficult for all of us, but we will manage. I'm sure we will manage. And feel free to send me emails anytime you want. And I'm very, very pleased that we started this work. Thank you so much to all of you. Thank you. Have a good day, and I see you all on Friday. Bye-bye. So we just stop.